Welcome, dear listener, to a tranquil exploration of one of the universe's most profound and elegant principles, the universal speed limit, often known as the speed of light. So before we get started, take a moment to like the video and subscribe, but only if you actually enjoy this type of content, and let me know where you are listening from and what time it is. It is truly wonderful to read comments and learn more about people. Now, settle in, find a comfortable position, and let your mind gently drift with the concepts we're about to uncover. There's no rush here, just a calm journey into the heart of physics. Today, we're going to understand why light, and indeed anything in our universe that has no mass, travels at a very specific, unchanging speed, and why nothing can ever exceed it. It's a concept that might seem counterintuitive at first, but with a gentle approach, we'll reveal its beautiful simplicity. Let's begin by setting the stage, understanding what we mean by the speed of light. When we talk about the speed of light, we're not just talking about the speed at which photons, the tiny packets of light, zip across the cosmos. We're talking about a fundamental constant of the universe, a cosmic speed limit that applies to everything. Imagine for a moment that you're in a car, driving on an open road. You press the accelerator, and the car goes faster. You press it harder, and it goes even faster. It seems intuitive that with enough power, you could keep accelerating indefinitely, reaching any speed you desire. But the universe, in its elegant wisdom, has a different plan. The speed of light in a vacuum, often denoted by the letter c, is approximately 299,792,458 meters per second. That's nearly 300 million meters every single second, or roughly 186,000 miles per second. To put that into perspective, light can travel around the Earth more than 7 times in a single second. It's incredibly fast, almost unimaginably so. But here's the crucial part, it's not just a speed, it's the speed limit. It's not a suggestion, it's a law, woven into the very fabric of spacetime itself. The constant nature of light speed, relativity's bedrock. Let's ease into our first key concept, the constancy of the speed of light. This is perhaps the most revolutionary idea that emerged from Albert Einstein's special theory of relativity, published in 1905. Before Einstein, people generally believed that speeds were always relative. Think about this, if you're on a train moving at 50 miles per hour, and you walk towards the front of the train at 3 miles per hour, someone standing still on the ground would see you moving at 53 miles per hour, 50 plus 3. This is simple addition of velocities, and it makes perfect sense in our everyday experience. This is called Galilean relativity. But what if you shine a flashlight while on that train? According to our everyday intuition, if the train is moving at 50 miles per hour and the light from your flashlight travels at c, then someone on the ground should see the light moving at c plus 50 miles per hour, right? This is where Einstein's genius, and the universe's surprising truth, comes in. He proposed, and it has been rigorously tested and confirmed, that the speed of light in a vacuum is the same for all observers, regardless of their own motion. Let that sink in for a moment. It means that whether you are standing still, or zooming past at incredible speeds, if you measure the speed of light coming from a source, you will always get the same answer, c. It doesn't matter if the light source is moving towards you, away from you, or is stationary. The speed of light remains constant. This is profoundly different from anything else we experience. It's like saying that no matter how fast you throw a baseball, everyone sees it moving at the same speed, which we know isn't true for a baseball. But for light, it is true. Imagine you're standing on the Earth, and a spaceship zooms past at half the speed of light, a speed we'll call 0.5 c. The astronaut inside the spaceship turns on a powerful laser beam. You, on Earth, measure the speed of that laser light. You might expect it to be 1.5 c because of the spaceship's motion. But no, you would measure it as exactly c. And here's the kicker, the astronaut inside the spaceship, moving along with the laser, would also measure the light traveling at exactly c. Neither of you would measure it as faster or slower than the universal constant. This is the cornerstone of special relativity. The speed of light is absolute. This constancy of the speed of light is not just a quirky observation, it's a fundamental property of the universe. It's what causes many of the strange and wonderful relativistic effects we hear about, like time dilation and length contraction. This means that light doesn't add its speed to the speed of its source. It simply travels at c. This fundamental constancy is our first clue as to why nothing can exceed it. If it were possible to go faster than light, then this absolute constancy would be violated, and the very structure of our understanding of space and time would unravel. So, to recap this initial thought, the speed of light in a vacuum is a universal constant. It does not change based on the motion of the observer or the source. It is always c. This is a deeply counterintuitive idea, but it's a bedrock principle of how our universe operates. Energy and mass, the E equals mc squared connection. Now, let's gently transition to thinking about mass and energy, and how they relate to this cosmic speed limit. This will lead us closer to understanding the intrinsic reason for light's unique speed. The relationship between mass and energy is perhaps the most famous equation in all of physics, E equals mc squared. This equation, also derived from special relativity, provides the deepest insight into the light speed limit. Let's break down this famous formula in a calm and accessible way. E stands for energy. This is the total energy contained in an object. M stands for Massachusetts. This is the amount of matter in the object. C superscript 2 is the speed of light, squared. The equation E equals mc squared tells us that mass and energy are two interchangeable forms of the same thing. They are not separate entities, they are deeply connected. A small amount of mass, m, contains a tremendous amount of energy, E, because the conversion factor is c squared, which is a very, very large number. Now, why does this matter for the speed limit? As an object with mass begins to move, its total energy increases. This is kinetic energy, the energy of motion. In classical physics, we calculate this using simple formulas. But as the object approaches the speed of light, the classical formulas break down, and we must turn to relativity. In relativity, as an object moves faster and faster, two things happen simultaneously. Its kinetic energy, energy of motion, increases dramatically. Its relativistic mass also increases. Yes, you heard that correctly. As an object accelerates, its mass effectively increases. It doesn't mean that the number of atoms in the object changes, but the object's resistance to further acceleration increases. It becomes harder and harder to push. Imagine pushing a toy car across a table. It's easy. Now imagine pushing a freight train. It's incredibly difficult. This difficulty in changing its motion is what we call inertia, which is directly related to mass. As you push an object to go faster, you are adding energy to it. According to E equals mc squared, any added energy must manifest as added mass. The faster the object goes, the more energy you have put into it, and therefore, the more massive it becomes. Let's trace this journey towards c. You start accelerating a particle. You put in a small amount of energy. Its speed increases, and its mass increases slightly. You put in more energy. Its speed gets higher, and its mass increases more significantly. As the speed approaches 90% of the speed of light, 0.9 c, the mass is already more than double its resting mass. As the speed creeps closer, say to 99% of the speed of light, 0.99 c, the mass becomes nearly 7 times its original mass. The closer you get to the ultimate limit, the more energy is required to achieve even a tiny increase in speed, because that energy is increasingly being converted into mass, making the object heavier and more resistant to further acceleration. This is the central physical block. As the object approaches c, its relativistic mass tends toward infinity. The infinite energy problem. The reason light's speed is the absolute limit is because reaching it would require an infinite amount of energy. Let's explore that idea of infinite energy. If an object with mass, no matter how tiny, even a single electron, were to reach the speed of light, its mass would become infinite. Think back to our equation, E equals mc squared. If the mass, m, becomes infinite, the total energy, E, required to achieve that speed must also be infinite. And as far as we know, there is no such thing as an infinite source of energy in our finite universe. You can build the most powerful engine imaginable. You can harness the energy of 1,000 stars. You can turn all the known mass in the observable universe into pure energy. Even with all that, you would only reach 99.999% of the speed of light. You would never cross the threshold. You would always fall infinitesimally short, because that final step, going from an unimaginably high speed to the speed of light, requires an infinite expenditure of energy. The mass increase is the universe's ultimate brake pedal. So, for any particle that has rest mass, meaning it has mass when it is sitting still, it is physically impossible to reach the speed of light. This is not a limitation of our technology, it is a limitation of the universe itself, defined by the beautiful relationship between energy and mass. Now, this leads us to the critical distinction: what about light itself? Why does light travel at c? Light is made of photons. And the photon has a crucial characteristic: it has zero rest mass. Since the photon has no mass to begin with, the rule that says mass goes to infinity doesn't apply to it. If a particle has no mass, it is mandated by the laws of physics to travel at the speed of light, c. It's an all-or-nothing situation. Any particle with mass must travel less than c. Any particle with zero mass must travel at c. The photon is the universe's perfect example of a massless particle. It is born moving at c, and it can never slow down, unless it interacts with matter. It exists only in the state of motion at the absolute speed limit. If a photon were to slow down, even slightly, it would suddenly have a mass greater than zero, which would then require it to slow even more, creating a paradox that violates the conservation laws of energy and momentum. In essence, light doesn't choose to go at the speed of light, it is the speed of light. C is the universal constant that dictates the conversion of mass to energy, and the photon is the particle that perfectly embodies that constant because it has no mass to hold it back. So, the rule is elegantly simple: if you have mass, you can't reach c. If you don't have mass, you must travel at c. This is the profound reason why light can't travel faster than the speed of light. Because the speed of light, c, is not just a velocity for light, it is the defining constant of the universe that determines the relationship between space, time, mass, and energy. It is the ceiling, the absolute ultimate limit, that all particles with mass can only approach, and that all massless particles must define. Let this idea settle comfortably in your mind. The laws of physics themselves ensure this limit. It's an elegant, self-consistent system that prevents the paradox of infinite energy and infinite mass. We'll continue this exploration in a moment by looking closer at the strange effects that proximity to C has on time and space. Let's continue our peaceful journey into the strange landscape of high-speed physics. We've established the unshakable truth that the speed of light, c, is an absolute constant, and that any object with mass is prevented from reaching it by the impossible requirement of infinite energy. Now, let's explore the equally fascinating consequences of approaching this speed limit. The constancy of c forces a beautiful and bizarre transformation upon the two things we often take for granted, time and space. Remember our astronauts zooming past Earth in a spaceship at a very high velocity, maybe 0.9 c. From their perspective, inside the ship, everything feels normal. They're aging, clocks are ticking, and their coffee cup falls straight down. But from our perspective, watching them from Earth, their reality appears dramatically warped. This warping takes two forms: time dilation and length contraction. Both are the universe's way of ensuring that the fundamental constant, the speed of light, is always maintained for all observers. Time dilation, the stretching of time. Time dilation is the phenomenon where time slows down for an object that is moving relative to an observer. The faster an object moves, the slower its time progresses. Let's use an analogy, a gentle thought experiment called the light clock. Imagine the astronaut has a special clock. This clock doesn't use gears or springs, it uses a single photon of light bouncing up and down between two mirrors. Every time the photon hits the top mirror and returns to the bottom, the clock ticks once. This is the simplest, most fundamental clock we can imagine, as it relies entirely on the speed of light, c. Astronaut's view: the astronaut sees the photon moving straight up and straight down, covering a certain short distance between the mirrors. They measure the time for one tick. Earth observers' view: now, we watch the astronaut's clock as the ship zooms past. Because the ship is moving, the photon's path looks different to us. Instead of going straight up and down, the photon has to travel a diagonal path. The mirrors themselves are moving forward while the light is traveling between them. The diagonal path is clearly longer than the straight up and down path. Here is the crucial part: since the speed of light, c, must be the same for both the astronaut and us, the universal constant, if the light has to travel a longer distance, it must take a longer amount of time. Therefore, we observe the astronaut's light clock ticking slower than our own. Time itself has dilated, or stretched, for the moving system. If the astronaut travels at 0.87 c, we would observe their time running at exactly half the speed of ours. If they flew for 10 Earth years, they would only age 5 years. Their clock would only record 5 years. This isn't a mechanical error, it's the nature of reality. Time must slow down in order to preserve the constancy of the speed of light. If time didn't slow down, then for the longer path we see, we would have to measure the photon traveling faster than c, which we know is impossible. Reinforcement: time dilation is the universe adjusting the flow of time for a moving object so that every observer, no matter how fast they are going, still measures light moving at the constant speed, c. It is a fundamental warping of time itself, a necessary consequence of the universal speed limit. Length contraction, the squishing of space. Hand in hand with time dilation is the concept of length contraction. This is the phenomenon where a moving object appears shorter in the direction of its motion, relative to an observer at rest. Once again, this is the universe working to maintain the absolute speed of light. If time is slowing down for the moving object, space, or the length of the object, must also change to keep things consistent. Let's imagine the astronaut is carrying a 100-meter-long measuring stick aligned with the direction of the ship's travel. Astronaut's view: the stick is 100 meters long. Earth observer's view: as the ship zooms past at a relativistic speed, we measure that same stick to be shorter than 100 meters. If they are moving at a very high speed, say 0.99 c, the stick might appear to be only about 14 meters long. The length of the object contracts, or squishes, in the direction of motion. Why does this happen? The length must contract precisely to compensate for the time dilation. When we combine the slowing of time and the shortening of distance, the fundamental equation that defines speed equals distance/time, always yields the same result for the speed of light. Imagine the ship is trying to cross a 100-meter gap. The astronaut measures the gap as 100 meters, and their time slows down to cross it. We, on Earth, measure the time slowing down and the gap, the ship's length, contracting. When we crunch the numbers using the formulas of relativity, both observers, despite their completely different measurements of time and distance, agree on one crucial thing: the speed of the light inside the ship is c. Reinforcement: Length contraction is the universe adjusting the length of an object for a moving observer, again, to ensure that the speed of light remains the constant c. Time and space are not fixed backdrops, they are flexible, interconnected elements that stretch and compress based on motion, acting like a protective shield around the speed limit. A unified reality, space-time. These effects, time dilation and length contraction, show us that time and space are not independent. They are intrinsically linked into a single, four-dimensional fabric called spacetime. It is through the warping of this fabric that the constant speed of light is maintained. Think of your current movement through this four-dimensional spacetime. You are constantly moving through it. You are moving through time at a constant, steady rate, that's how you age. You might also be moving through space, walking, driving, or just riding the Earth's orbit. The total amount of your motion through spacetime is always the same. When you are standing still, you are putting all of your motion into the time dimension. You are aging fast, but moving through space at zero velocity. When you start to move in space, to accelerate, you are diverting some of that total, fixed motion away from the time dimension and into the spatial dimensions. As you approach the speed of light, you are putting almost all of your motion into the spatial dimensions. Because the total motion is a fixed constant, which is c, this means there is almost no motion left for the time dimension. This is why your time slows down. Your total movement through spacetime is conserved, but it is redirected. The speed of light, c, is the ultimate conversion factor between movement in space and movement in time. It is the limit where all of your motion is spatial, and time essentially stops. The reason light can't go faster than c is because c represents the point where all possible movement is converted into spatial travel, leaving zero movement in the time dimension. There is simply no other dimension or variable left to borrow motion from. Once a particle is traveling at c, it is moving at the maximum possible rate through the structure of the universe. And this brings us back, one final time, to the photon, the particle of light. Since the photon has zero mass, it is not constrained by the energy/mass relationship we discussed earlier. It is a pure wave/particle of the field. And because it travels at c, it experiences the ultimate relativistic effect. Time does not pass for a photon. If you could ride a photon, your journey would be instantaneous, no matter how far you traveled. To a photon, the distance between the source and the destination is contracted to zero, and the time elapsed is zero. Light exists outside of the flow of time as we experience it. This is the beautiful, self-consistent world of relativity, all stemming from the single, unyielding fact: the speed of light, c, is the universe's absolute speed limit, enforced by the stretching of time, the contraction of space, and the fundamental link between mass and energy. We will next explore what might happen if something could break this limit, and why the consequences would shatter our understanding of cause and effect. Take a moment to breathe, and let these incredible ideas about the flexibility of time and space settle gently into your mind. We have calmly established that the laws of physics, enforced by the requirement of infinite energy for massive objects and the warping of spacetime for all objects, prohibit anything from accelerating to or past the speed of light. But let's allow our minds a moment to wander into the realm of the impossible and ask, what if something could travel faster than light? What would be the catastrophic consequences for our universe? The answer lies in the fundamental concept of causality. Causality, the law of cause and effect. Causality is the bedrock of our reality. It's the simple, intuitive rule that an effect must always occur after its cause. If you flick a light switch, the cause, the light turns on, the effect, a tiny moment later. The cause always precedes the effect in time. If an object, hypothetical or real, could travel faster than light, this fundamental order of cause and effect would be completely shattered, leading to a host of logical paradoxes. Think about it this way: the speed of light, c, is more than just a speed, it is the ultimate messenger. Nothing can travel or influence an event faster than the speed of light. This means that a cause can only influence an effect within what is called its light cone, the region of spacetime reachable by a signal moving at c or slower. If you send a signal, the cause, faster than light, the rules of relativity predict that, for certain observers, that effect could appear to occur before the cause. Let's use a mental exercise. Imagine our high-speed spaceship, now somehow moving at twice the speed of light, 2c. The astronaut inside sends a message to Earth, cause, sending the message. Astronauts view, they send the message at time t_1, and it arrives at Earth at time t_2, where t_2, t_1. Simple and logical. Earth observers view, because the ship is moving so fast, relative to Earth, the rules of relativistic transformation, Lorentz transformations, predict that an observer on Earth could calculate the arrival time t_2 as being earlier than the sending time t_1. The message arrived before it was sent. This is a temporal paradox. The effect, receiving the message, precedes the cause, sending the message. The grandfather paradox, applied to physics. This violation of causality leads directly to paradoxes, the most famous being the grandfather paradox. In its classic form, if you travel back in time and prevent your grandfather from meeting your grandmother, you were never born, so you couldn't have traveled back in time in the first place. Faster-than-light travel is, mathematically, equivalent to a limited form of time travel. The ability to send information or matter FTL, faster than light, allows for the possibility of influencing the past, which creates unresolvable contradictions in the present. The universe, based on everything we observe, is built on a foundation of causality. If you could send a signal FTL, you could, in principle, send a message back to the past, telling a system not to send the initial message. The message would be sent and not sent simultaneously, a logical absurdity that shatters the very idea of a predictable, consistent reality. Reinforcement, the speed of light is the maximum speed of causal influence. If anything exceeded it, the sequence of cause and effect would become observer-dependent, destroying the universality of physical laws and leading to logical paradoxes that violate the fundamental structure of time itself. For the universe to be logically self-consistent, c must be the absolute limit. The mythical tachyon. For decades, physicists have contemplated the possibility of a hypothetical class of particles that do travel faster than light, tachyons. The equations of relativity don't absolutely rule out the existence of particles that always travel faster than c. However, if tachyons exist, they would have some very strange properties. Imaginary mass, tachyons would possess what is called imaginary rest mass. This is not a physical property we can grasp easily, but it's the mathematical way of saying they have zero mass and are fixed at FTL speeds. The FTL floor, just as massive particles are limited by the FTL ceiling, tachyons would be limited by the FTL floor. They could never slow down to the speed of light, c, because slowing down would require an infinite expenditure of energy. This is the opposite of massive particles. For an object with mass, infinite energy is required to accelerate to c. For a tachyon, infinite energy is required to decelerate to c. A tachyon travels fastest when it has the least energy. A tachyon slows down, travels closer to c, as it gains energy. If a tachyon lost all its energy, it would become infinitely fast. But even if tachyons were found, they would still violate causality. The discovery of a tachyon would be the simultaneous discovery of a physics-based mechanism for sending signals into the past, causing the causal paradoxes we just discussed. Because no experimental evidence of tachyons has ever been found, and because their existence leads to such profound logical contradictions, most physicists assume they do not exist. Their non-existence is a subtle, yet powerful, confirmation that the speed of light is indeed the universal, unyielding boundary. Reinforcement, the universe appears to only allow for two types of particles, those with real mass, which must travel less than c, and those with zero mass, which must travel at c. There is no known room for the intermediate state, or the hypothetical faster state, without violating causality. The absence of FTL phenomena is the universe's quiet confirmation that the past must precede the future. We've now covered the pillars of the speed limit, its constancy, its enforcement via energy/mass conversion, and its role in protecting causality. In our next section, we will gently explore the concept of the field and how light arises naturally from the properties of the electromagnetic force. Settle in, and let this peaceful understanding of time and cause and effect wash over you. Let's shift our gentle focus now from the dramatic effects of high speeds on mass and time to the very essence of light itself. We need to understand the medium through which light travels and the nature of the particle that must travel at this ultimate speed. We've established that the photon, the particle of light, has zero rest mass. This is the physical characteristic that exempts it from the infinite energy barrier we discussed earlier. But why is its speed exactly c? To answer this, we must look at the electromagnetic field. The universal fabric, the electromagnetic field. Imagine the universe is not just empty space, but is permeated by a continuous, invisible fabric called the electromagnetic field, EM field. This field is the source of two of the four fundamental forces, electricity and magnetism. When you rub a balloon on your hair, you're interacting with the electric part of the field. When you use a compass, you're interacting with the magnetic part of the field. These two aspects are inextricably linked, they are two sides of the same coin. A changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. Now, think about light. Light is simply a disturbance or a ripple in this electromagnetic field. It is a self-sustaining wave of oscillating electric and magnetic fields traveling together at a specific velocity. The speed at which any wave travels through a medium is determined by the properties of that medium. Think of sound waves. The speed of sound is determined by the stiffness and density of the air or water it travels through. Similarly, the speed of light, c, is determined by two fundamental properties of the vacuum of space, which is essentially the stiffness and density of the EM field itself. These properties are electric permittivity epsilon. This measures how easily an electric field can propagate through a vacuum. Magnetic permeability mu. This measures how easily a magnetic field can propagate through a vacuum. These two constants are built into the fabric of space itself. They are not arbitrary numbers, they are fundamental constants derived from the deepest understanding of electricity and magnetism, captured in the beautiful equations formulated by James Clerk Maxwell in the 1860s. Maxwell's equations and the inevitable speed. Before Einstein and before the concept of the photon was fully developed, Maxwell's equations described how electric and magnetic fields interact. When Maxwell combined his equations, he found a remarkable and unexpected result. They naturally predicted the existence of an electromagnetic wave that must travel at a specific, fixed speed. When you plug in the measured values for the electric permittivity, epsilon, and the magnetic permeability mu into the formula derived from Maxwell's equations, the resulting speed is exactly what we call the speed of light, c. c equals 1 divided by square root of mu naught times epsilon naught. This is a profoundly important revelation. It means that the speed of light is not a coincidence or a measured variable that changes, it is a direct, mathematical consequence of the fixed, unchanging properties of the vacuum of space. Reinforcement, the speed of light, c, is an intrinsic constant of the vacuum. It is determined by the fundamental properties of the electromagnetic field, mu and epsilon. This constant speed is the only speed at which a massless electromagnetic ripple can sustain itself and propagate through the universe. Why light cannot travel faster? This simple formula explains why light cannot travel faster than light speed from the perspective of field theory. The EM field is the medium, the vacuum itself acts as the medium for light. The speed of light is the maximum speed that a disturbance can travel through this field, dictated by the field's fixed characteristics. The constants are unchangeable, Since mu and epsilon are constants, they don't change whether you're standing still or flying past. The resulting speed, c, must also be a constant for everyone, everywhere. This ties back perfectly to Einstein's first postulate of relativity. If a photon tried to travel faster than c, it would be like trying to force a sound wave to travel faster than the speed of sound in air, without changing the air's properties. It is simply physically impossible within that medium. The EM field structure won't allow it. The photon's unwavering path. We can now solidify our understanding of the photon. The photon is the quantum of the electromagnetic field. It is the minimal possible packet of that traveling field disturbance. Because it is a pure manifestation of the field and has no mass, it is not subject to the slowdown constraints of massive objects. It cannot exist in a state of rest. The moment a photon is created, when an electron drops to a lower energy level, for example, it instantly begins moving at c. The universe's constant motion through spacetime that we discussed earlier is channeled entirely into its spatial velocity. It is forced to move at the speed of the field disturbance itself. If the properties of the vacuum, mu and epsilon, were different, the speed of light would be different. But the laws that set c as the universal limit for massless particles would remain exactly the same. Reinforcement: the speed of light is not an arbitrary number, it is a mathematical necessity derived from the fixed constants governing the electromagnetic field. Light, being a pure wave of this field, is forced to travel at this constant speed. To travel faster, the light would have to defy the fundamental electrical and magnetic properties of space itself, which is impossible. We'll take a quiet moment now before moving on to explore the practical implications and evidence of this speed limit, looking at cosmic rays and particle accelerators. Let the simplicity and elegance of Maxwell's connection between light, electricity, and magnetism bring a sense of calm understanding. Having explored the theoretical barriers, infinite energy, space-time warping, and causality paradoxes, let's ground our understanding in the real world. We are not just relying on abstract theory. Every experiment ever performed, particularly in the realm of particle physics, confirms the absolute reality of the speed limit, c. The particle accelerator evidence. The most compelling, direct evidence for the speed limit comes from particle accelerators, such as the Large Hadron Collider, LHC. These machines are essentially the ultimate speed testers in the universe. In these accelerators, physicists take subatomic particles, like protons or electrons, which have mass, and use immensely powerful electromagnetic fields to accelerate them to speeds incredibly close to c. Let's recall the principle of mass increase. The closer a particle gets to c, the heavier it becomes, requiring more and more energy for even a tiny bump in speed. Initial acceleration: when a particle is moving slowly, a small amount of energy results in a large increase in speed, just like pushing a toy car. Approaching c, as the particles reach about 99.9999% of the speed of light, physicists must continue pumping energy into them. But now, that huge amount of added energy no longer translates into a measurable increase in speed. Instead, the energy is almost entirely converted into relativistic mass. The experimental results are perfectly consistent with Einstein's predictions. Speed plateau: no matter how much more power they feed into the accelerator magnets, the particles refuse to cross the c boundary. Their speed effectively plateaus at this limit. Mass spike: the energy is being absorbed, but its manifestation is the dramatically increased mass of the particles. Protons in the LHC, for instance, are accelerated so close to c that their mass increases by a factor of over 4,000 times their rest mass. This is the universe saying, you can have all the energy you want, but you cannot violate the speed limit. The accelerator experiments serve as a continuous, robust verification that the speed of light is not only a theoretical limit but a physical reality that cannot be surpassed. Reinforcement: particle accelerators demonstrate empirically that as an object with mass approaches the speed of light, the energy used to accelerate it is converted into relativistic mass, preventing the object from ever reaching c. The speed limit is physically enforced by the universe's mechanics. Cosmic rays and the energy limit. The particles in our accelerators are fast, but the fastest moving particles known in the universe are cosmic rays. These are high-energy particles, mostly protons, that originate from distant galaxies and powerful events like supernovae. They are accelerated naturally to speeds far greater than anything we can achieve on Earth. Some cosmic rays have energies millions of times greater than the highest energy protons produced in the LHC. These are the ultra-high-energy cosmic rays, UHICRs. Yet, when we measure their speed, we find that these particles, too, fall infinitesimally short of c. They might be traveling at 0.99999999999999999999999999999 c, but they never hit the full speed of light. If these particles, driven by the most energetic phenomena in the universe, cannot break the speed limit, it provides a powerful cosmological confirmation that the limit holds true under all conditions, everywhere in the cosmos. Cherenkov radiation, the local exception. Now, let's address a gentle clarification to avoid confusion, the idea of Cherenkov radiation. You may sometimes hear that particles can travel faster than light. This statement is only accurate under a very specific condition and does not violate the cosmic speed limit, c. The speed of light, c, is the speed in a perfect vacuum. However, when light travels through a medium, such as water or glass, it interacts with the atoms and molecules in that medium, effectively slowing down. The speed of light in water, for example, is about 0.75 c. Cherenkov radiation occurs when a charged particle, like an electron, travels through that medium, the water, at a speed faster than the speed of light in that specific medium, but still significantly slower than the universal speed limit, c. Imagine a boat moving faster than the ripples it creates in the water. It creates a shock wave. Cherenkov radiation is the optical equivalent of a sonic boom. The particle is traveling faster than the local speed of light, and the electromagnetic disturbance it creates piles up into a characteristic blue glow. This is a beautiful and real phenomenon, often seen in nuclear reactors where fast electrons travel through the surrounding water. But critically, the particle is still traveling slower than the universal constant c. It is only faster than the local, slowed-down speed of light in the water. Reinforcement, the universal speed limit, c, remains absolute. Local phenomena like Cherenkov radiation, where particles travel faster than light in a specific medium, are consistent with the limit, as the particles are still much slower than c in a vacuum. This confirms that c, the vacuum speed, is the only true, unbreakable limit. We are nearing the end of our tranquil exploration. In our final section, we will gently summarize these concepts and reflect on the philosophical implications of this absolute speed limit. Philosophical reflection and the limits of knowledge. We now arrive at the final, reflective segment of our journey. We have explored the hard science of why light speed is the limit, but this concept carries profound philosophical implications for how we perceive reality, knowledge, and the very structure of the universe. The universe's design, an ordered cosmos. The absolute limit of c ensures that the universe is predictable and ordered. Without this limit, as we discussed with the causality paradox, information could travel backward in time, making all cause and effect relationships meaningless. Every event would be susceptible to instantaneous influence from any other event, past, present, or future. The speed of light, therefore, acts as the information gatekeeper. It ensures that what happens on Earth today cannot instantly be influenced by an event that happens on the star Alpha Centauri tomorrow. The time it takes for light, or any signal, to travel the 4.4 light-years from Alpha Centauri to Earth guarantees that the events are causally separated and can only influence each other in the correct temporal sequence. This is what allows science to function. Physics is based on observing a cause and predicting its effect. If the time order of events were relative and changeable based on motion, our physical laws would break down. The consistency of the speed of light is the reason we can confidently predict the movement of planets, the behavior of electricity, and the energy output of the sun. The limit ensures cosmic stability. Reinforcement: the speed of light is not just a physical constant, it is the fundamental law protecting causality. It ensures a universal, consistent order of cause and effect, which is necessary for a predictable and understandable cosmos. The limit of human experience. The cosmic speed limit also defines the limits of our knowledge and interaction within the universe. When we look up at the night sky, we are looking into the past. The light from the nearest star took over 4 years to reach us. The light from distant galaxies may have traveled for billions of years. When we observe an object 10 billion light-years away, we are seeing that object as it was 10 billion years ago. The speed of light dictates how much of the universe is observable to us. The farther away something is, the older the information we receive about it. Because the universe has a finite age, approximately 13.8 billion years, there is a distance beyond which light has not yet had time to reach us. This boundary is the edge of the observable universe. The speed limit, therefore, imposes a boundary on our immediate knowledge. It is a humble reminder that we are constrained by the speed at which information, light, can travel. We can only know what the universe was, not what it is right now, on cosmic scales. There is an inherent, unbridgeable time delay built into our perception of the wider cosmos. Reinforcement: the speed of light governs the size and age of the observable universe. It imposes a delay on cosmic information, meaning that all astronomical observation is fundamentally a look into the past. Reflection on the impossibility. Let's return, finally, to the core question: why can't light travel faster than the speed of light? It is because the speed of light, c, is not simply a velocity assigned to a specific particle, it is the maximum exchange rate between time, space, mass, and energy. It is the built-in, immutable characteristic of the fabric of spacetime itself. Light, being massless, must travel at this rate because it has no intrinsic mass to resist the acceleration, and c is the natural speed of its medium, the electromagnetic field. Any particle with mass, even if it were to acquire infinite energy, can only approach c, because that energy converts into mass, creating an ever-increasing barrier against the final step. The speed of light is the ultimate benchmark of motion. It is the speed where the flow of time ceases, and distance collapses to zero. There is no faster state of motion possible because there is no more time left to trade for speed, and no more energy available in the universe to overcome the infinite mass barrier. The universe is built elegantly around this constant. E equals mc squared, and the principles of relativity show us that c is not just a speed to be measured, but the foundation upon which existence is structured. Find comfort in this elegant limitation. The fact that the universe has an absolute speed limit makes it a logical, stable, and predictable place. It is a sign of deep harmony in the laws of nature. Thank you for joining this tranquil exploration of the speed of light. May the constancy of c bring you a sense of peace and wonder.